acknowledgement in place. So first of all, really want to thank the Intel guys and the Zen committee for giving us the opportunity to come and present. And it's my first time here, so please be gentle. So we have, in addition, we're co-presenting with Cisco. So Don Banks and Phil Winterfield from the research division are here today. They're going to take the second side of this, second part of this pitch. And again, thanks for, really appreciate you presenting with us. So we've been working together for the past couple of years on trying to make Zen more suitable for embedded and comms workloads. And I'm about to talk about what it really means, because we've talked a lot about, I heard Ian, and I heard a lot of talk about schedulers, and heard Ian talk about embedded and communications, or at least about embedded. I think there may be a slight discrepancy with what we really mean with embedded, and that's what we're about to talk about. So I'm going to talk about some usage models. How do you extend Zen really into small handheld kind of devices to all the way into high-end servers? How do you do that? What are the requirements? I'll talk a little bit about specific VMM requirements that you may have, and we're going to talk about some benchmarks. And then I'll leave it to Don, who's going to give you some real-life cases on what they need in order to be successful in terms of Zen deployment and these kind of things. Right, so I work for the embedded division, and Intel has a embedded division, believe it or not. So anybody care to have a guess to why you'd want to deploy a virtual solution or a VMM in any one of these devices? Security. But there's much more a fundamental reason to why you want to do this. Isolation is really good. That's excellent. This is exactly for most of these kind of cases why we do this. So given an Atom-based design all the way at the low end of like a media phone kind of device, you really need isolation. And in some cases, some of these designs, and they don't necessarily use Atom, maybe they use an ARM design of some sort, they combine a second controller to essentially do the radio head. Yeah, so you get a call coming in, and maybe you're doing something in an application at the same time, but you have to take that call. And what we're proposing is to use something like a VMM to do this kind of thing. And we've worked with some commercial vendors in the past, and they've built some usage models around it, and they built some capabilities. It'll be far interesting for the embedded division that I work for to extend Zen in that kind of direction. So that's sort of the topic of discussion today. We have parts, so we adopt, the division I work for doesn't necessarily build these CPUs themselves, but they generally adopt parts and put them on a roadmap and give them long life support. We do that for Atom-based designs, we do that for the general core architecture, and we do that all the way for the Xeon-based designs. That makes it kind of tricky to design one VMM solution that scales all the way. However, we think that Zen has a really good potential to fit in the majority of these kind of segments. So what does that mean from a VMM perspective? What is the kind of capabilities you really need? And I kind of talked about that earlier on, and actually was kind of really encouraged to see the past couple of days, or at least yesterday, we talked a lot about footprint control. Well, if you have an Atom design with a relatively small amount of memory, or earlier on an ARM design with a small amount of memory, your footprint needs to be small. There's no doubt about it. Having that control is really important. The other thing what we do, and again I heard a lot of talk about scheduling control, and I'll talk about that in a minute as well. Specifically for single core designs, it is absolutely crucial that you have better scheduling capabilities. And we have some research in process that I'll talk about it in a little bit. But the point is, single core designs, you need a better scheduler. So what we do in these other designs, on the medium end and on the high end, we generally pin virtual machines to a certain core to guarantee execution. So that's the way we get around that kind of problem. These commercial guys, for instance, industrial computing, where they do robotics and medical imaging, where they control some sort of like a CAT scan equipment, where they control some sort of a robot arm. they generally have some sort of a graphical user interface for an operator to control that, and that generally runs Windows or something like that. So they really like the thought of, hey, can't we consolidate some of those control aspects on a dual-core kind of part and use a virtual machine monitor to do kind of thing. And there are commercial solutions that do this. The way, and obviously you need real-time performance in those kind of environments. The kind of real-time performance they need can be less than 10 microseconds. And that's pretty significant. The only way you're going to approach that today is by essentially pinning. And that's what these guys do. They generally do a mixture of, they don't necessarily virtualize everything. They generally have like a set of mailboxes. Yeah, they share memory between, much like the ground table mechanisms that you have in Zen. That's the kind of thing these guys use to achieve this. And then on top of that, they embed the real-time operating system, essentially becomes the hypervisor. So that's sort of what that picture means. But most part of this talk going forward, we're going to concentrate on this kind of thing. And I think here we have a much better chance of being successful with Zen. And that's mainly because of the flexibility Zen offers and the scalability, and there are some things that are missing, things like REST features. And that's the kind of stuff that Don's going to talk about in a bit. So I think this is sort of summarizing the comms value proposition, I think. One of the issues you may not be aware of is the tons of legacy that a lot of our telecommunication equipment manufacturers deal with. Avaya must be dealing with that kind of problem as well. You know, I know that some of your not only your codecs, but I think you call it the WAD or something like that, WAD. It's a big chunk of single-threaded code that's been developed over 20 years. Some of these guys aren't around anymore. How are you going to thread that? How are you going to make that run efficiently? And some guys just don't bother. They stick it in a virtual machine and they maybe run multiple instances. So that's absolutely a key value proposition. It's maybe taken a while, but the past year, 2 years, every single telecommunication equipment manufacturer has some sort of a Zen or KVM or VMware. They have some sort of a project that deals with these kind of issues of moving these big single-threaded pieces of code into a virtual machine and tying them to a core. So it's consolidation of legacy. That's got to be by far the biggest advantage. And then going forward, they want to deploy new services. Right? They want to be able to respond to some new demand. Maybe they want to deliver some sort of a voicemail virtual machine on top of a telecommunications device, that kind of thing. So I just want to share some research that we have. The way I shaped this pitch is more along the lines of giving you an insight of what kind of research we have going on. And maybe in 6 months or maybe in a year, we can come back and report out to where we got to with this kind of research. So what we've been doing is same as a lot of the other folks. We've been another team in the embedded group has been experimenting with the credit-based scheduler to see if we can essentially create that separation we need. Can we sustain a phone call at the same time when there is some sort of a piece of video being streamed? And then you need some element of quality of service. And in these kind of platforms, we don't necessarily have several cores. Yeah, we generally have a hyperthread or something like that. Maybe in the future we'll have dual core, but today we don't. And if we want to drive the power further down to make it fit into a cell phone or into something else, well, we'll maintain single core for quite some time. But then you need a scheduling algorithm that can deal with these kind of things. So I found the talks about scheduling very, very interesting today, and I wonder if we can cooperate in the future on these kind of things. So the specific group that I work for, I focus on packet processing. And we do a bunch of benchmarking on this forwarding thing. We love forwarding. We're practically obsessed with it. So every benchmark we run in our labs concentrate on how effectively we can move a packet into a platform and how we can move it back out. And it's to deal with products like wireless base stations or routers or telephony equipment, that kind of thing. So developed this very, very small runtime to essentially forward packets. And it's really, really efficient. Several hundred cycles to take a packet into main memory and to get it back out. And I won't share all the details right now. But the point is, if you're just forwarding, it doesn't buy you much. You really need to do something more. You need to inspect that packet, or a certain volume of the packets may go straight back out. But there may be another level of packets that you're interested in to have a look at. Yeah, you see a certain tag, or it's an HTML, or it's an XML packet you want to inspect. In those kind of environments, we're doing some research right now to use the ground tables, specifically the I/O rings, to essentially DMA straight into a ground table and then inform some sort of a Linux distribution that has some sort of an intrusion detection application. So that will do packet inspection. So that's the kind of setup we're working on right now. And this has been really, really promising. We see practically native performance, but there's a lot more research going on. When we scale this to 3, we're good. When we scale this to 4, we're all right. But when we scale this to 5 instances, we actually start seeing some performance degradation. And we need to do some more research to figure out why that is happening. But the point is, why do we do this? And Linux and other distributions have some really good intrusion detection applications. And there are a lot of existing applications that we don't want to port from here to here, because we want this just to do base forwarding. Yeah, and that's what virtualization buys us in packet processing. There's a lot of our customers have shown interest in this kind of thing. Yeah, so this is we'll probably, at least the team that I'm working on, the next year or so, we're going to spend a lot of time on this and a lot of research. And I wonder whether this is an interesting topic to perhaps bring back. And I'd love to have feedback from the folks in the room today, whether that is an interesting topic for future discussions. Go ahead.
In general, what you're describing here is just packets in, go through a thing, and back up, and just forward, right? So it's basically a linear bump in the wire.
Yeah, it is absolutely. It's a bump in the wire. Really important.
But there's what you're missing here is configuration with a forwarding decision, right? That is, which egress interface does the packet go out of, which is more of a switching decision. Is that part of what you're interested in?
It's not a switching decision. We make a decision, because imagine there are multiples of those fast paths behind here, right? And there is a switching decision. It's not a switching. You look at the IP header, and then you make a choice on what interface you're gonna send it out to.
There is an egress decision made.
Exactly.
Okay.
So the point is, if I had another hour, I'd go over it, because the point is that the Linux stack is inherently very, very crappy at moving packets. And that's kind of, I'll come to that in a second. I'll hold your question for one minute. So this is another piece of research which we're working on, and it's kind of linked to a power management study. So if you look at edge-based devices, and they generally have a power profile, and I split it into voice and data. This comes from some telecommunications equipment from the Intel network. We generally see this kind of curve for data, and we see this kind of curve for voice, and the area under the curve is the volume of data being moved. And you clearly see that there is obviously a geological aspect that goes along with that. The fact is that people come to work and they go home at the end of the day. That's the point is that a lot of those application stacks I was talking about earlier on, they're generally not power management aware. So if you were to take a proprietary operating system stack that generally runs a telecommunications equipment device, that is not power management aware. So it doesn't take advantage of ACPI. There is no power savings whatsoever. All the CPU silicon developers, we spend lots and lots of dollars on ACPI capabilities and power management capabilities. How do you expose that to these guys? And you generally can't. So virtualization gives us a really good additional benefit for the ability to realize power savings in those off peaks. And that's another project we've got going on right now. So just want to come back to, actually I'll do that after this slide. I just want to come back to your question in a second, what it really means in terms of forwarding. Other research we've going on is on a feature called direct cache access. And Jun and Alan and Don Duggar has been really helpful from the Intel team to try and get this ported to Xen. The issue with suffering, so this is an extract from the driver, we need to get, so DCA is a function that essentially allows us to push data from the NIC directly into cache, but you need to update the NIC device to essentially say, hey, you need to DMA in this particular cache belonging to this particular CPU. Well, when we run this call inside a VMM, it doesn't return the right CPU, obviously. So right now, we're contemplating with the idea of developing a new hypercall or modifying a hypercall that will essentially give us the real CPU ID of the core we need to DMA this into. So again, that's just a topic I'd like to put out there. If you have any ideas on how to do this effectively, please let me know. So this is what I really want to come back to in relationship to your question. This is why it's really important. You're saying, hey, this is a switching decision you make. It may not be a big deal, or it may be a big deal. This is why it will become a big deal. As we move to 10 gigabit Ethernet, in order to keep up with 64-byte line rate, you have roughly 200 cycles to essentially move that packet in and out the platform. That's not an awful lot of time. Right now, if you take the base Linux stack, it takes 3,000 cycles. So we've optimized that, and we looked in much more detail. We took a lot of the locks out of the forwarding path. We did a lot of optimized buffer management. We make sure that our structures are cache aligned, all sorts of stuff to the skbuff libraries in the Linux stack. And with that, we could get it down to roughly 1,300 cycles. But that's still not near enough to keep up with 10 gigabit line rate. So now we need to take a brief step back to that picture I showed earlier on, where we have that fast path, where we have that fast path OS we've developed to move packets around. That essentially does it today in roughly 300 cycles. And so that is a pretty impressive optimization we did at the time. And on top of that, it virtualizes really, really well. As long as we pin it to a CPU, we get native performance. So does that kind of get back to your question? Is that where you were heading?
It does. So this graph appears to be a purely software diagram, and any second generation CNA will have a programmable forwarding path which allows you to do a whole bunch of header processing in hardware, in which case you can get it kind of speed up that way. So though I buy into the curve, it's a purely software curve based on the Linux bridge curve.
Yeah.
Gosh, we know that is not optimized. So I think that there's a very interesting path here. The question actually I wanted to ask is whether or not you guys have looked at there's a new virtual switch being developed at openvswitch.org, which is already in the XCP code base.
Okay.
Okay? And what it has there is a programmable forwarding path. In the event that you have hardware that can do magic packet field identification, then you can make use of that. And so it separates the control plane forwarding plane stuff reasonably well. And it also will give an opportunity, hopefully, to inject hooks into the fast path so that in general you don't have to take every packet up through that path. You only suck up packets that needed additional processing. Through some arbitrary match on header field. So maybe, I think it matches currently on a 12 path. Okay. Anyway, I would love for you guys to take a look at that.
For sure.
Way suboptimal right now, but it's an interesting future development.
So we have our reservations about doing switching in domain 0, doing switching in the hypervisor. Honestly, we only just heard about it yesterday. Don and I had a...
Switching in domain 0.
Okay.
It's not. I mean, in general, it's a vSwitch. It just turns out most Xen implementations have a domain 0 where you run drivers, and then there's other stuff, right? But where this thing would run is completely independent decision. So, for example, you could run it as an IO node sitting in the middle of your server or your platform, servicing a bazillion back-end drivers for a whole bunch of guests. In which case, it's not domain 0. Domain 0 is just some management thing, right? Doing multi-threaded, and it can do magic stuff with PCI pass through NICs or indeed SRID virtual functions right through.
be a fantastic action, and I'm sure Don and I will be more than happy to look at that. So. Yeah. So I'm actually about to finish up. So I'm trying to get you guys out to lunch. Well, after Don, that is. So one thing I did want to share with you, unfortunately, the fast path forward in, like I said, we see some degradation after 3 to 4 guests. We still have to do some homework to why that is. When we take base forwarding, when we just look at the Linux stack and take packets in and out, this actually scales very, very well. So this is essentially the red line behind, the kind of lighter red line is essentially native performance, and we actually scale linearly along with that, which is really good. But the point is, under all circumstances, we use pass-through, so through VTD logic, and we use direct assignment to keep up with this. And honestly, in our environments, that is not an issue. Yeah, so if we take the DCA case, the direct cache access, just briefly back, just having a static call that says, hey, from this guest, we just want direct pass-through and want to have these packets straight into this particular cache is not an issue. But for a broader usage, some people may want to use direct cache access that actually scales. So if you reassign a virtual machine to another core, then that needs to migrate along. And right now, we have problems with doing that effectively. So I'm not taking questions right now. I want to ask Don to come up and finish this pitch, and then we can take more questions at the end of that. This is forward. This is forward. Good.
So as Edwin said, I'm Don Banks. Phil and I are with the Research and Advanced Development Organization in Cisco. And our job, or at least so my boss tells me, is to look at technology, develop prototypes, and then for our BUs, our business units, which are the organizations within Cisco that actually develop products, to push that technology out into those BUs that are interested and help them put a product out the door. So I'm going to take a product development point of view, or user's end point of view when I talk about this. Cisco has a wide variety of products across the various market spaces. In the past, what we've done is, in order to scale, we either produce multi-chassis or multi-card devices, and typically at the high end. At the low end, what we have done in the past is tend to push everything into a single OS, very often on a single core processor. There are, of course, scalability issues and some reliability issues with that approach. What we see with virtualization is that there are lots of opportunities to produce more scalable, more secure, more reliable products across the range, and to introduce features like software HA across the range. So we produce everything, I'm sure many of you are familiar with Cisco products, from low-end flip video and home routers up through branch enterprise, data center, and service provider routers. And then there's additional equipment like video and voice boxes, set-top boxes, security boxes, deep packet inspection boxes that look at packets or bumps in the wire. They look at packets and characterize them, tag them, so that later processing can do specific things with them, including perhaps load balancing at a later stage. Within this group of products, we think that virtualization can provide us a number of opportunities for unique products. So our hardware environment typically consists of a number of different types of processors, generally SoCs, ASICs, FPGAs, DSPs are used to enhance the forwarding plane processing. They're generally separate from the general purpose CPUs, although at the low end, all the forwarding is done in software. At the high end, the mid through high end, most of the forwarding is done with the aid of ASICs, SoCs, and FPGAs. So the forwarding data plane are split in most implementations. In some implementations, they're put together. But one of the things virtualization, for instance, allows us to do is look at maintaining that split and running that in separate VMs on one or more cores for each. The bandwidth for most of these routers is anywhere from multi-terabit to gigabit I/O. Typically, these days, gigabit is a requirement just about anywhere. The software environment is multi-OS, for better or for worse. We have a legacy OS called iOS that most of you probably know about. It's proprietary and it's single-threaded, single address space, unprotected, not a paged environment. We also have some Linux-based OSs and some OSs based on proprietary kernels. There are multiple VM models we see using, and that depends on the particular application space, and I'll talk about some of them in a little more detail, but some examples are integrated services routers. For example, you might integrate voice and data on the same box and use separate VMs to process voice and to process data. When a voice packet has to be shipped, it sends it to the data plane, and the data plane routes the packet appropriately, and similarly packets that come in go up. Distributed and load balancing is another application we actually built a POC for. HA is a very important issue in our space, and I'll talk about that in some detail later. Of course, memory processor and I/O bandwidth requirements vary greatly depending on the applications and the position of the box in the network. So, some of our requirements. First of all, we think Xen, after working with a number of vendors on a number of different processor architectures and a number of different hypervisors, we've come to the conclusion that Xen on x86 is the best solution that's out there, and there are a number of reasons for that. First of all, we need early support for prototype hardware, not only from third-party vendors, but also our own prototype hardware. That includes drivers and other modifications we need to make. We think it's the right architecture. Separation of DOM0 and the hypervisor and all the functionality in DOM0 that runs there is the right architecture. It's the architecture that was invented 40 plus years ago, and it's the architecture that most hypervisors have followed. Some haven't, and they have a number of issues, including trying to support a number of things they want to do. So we think open source Xen and Linux are critical to what we're doing. Reliability and serviceability, availability and serviceability. HA for guests is critical in our space. Non-disruptive stateful failover, along with non-disruptive in-service software upgrade, is critical to many accounts. All the way from service providers down to cable service providers, down to Walmart. They don't want their services to go down. So what I mean by non-disruptive is the network doesn't ever see a failure occur. The fault occurs and it's completely contained within the box. The box recovers. Anything out on the wire never sees the bump, except for, in some cases, depending on what the architecture looks like, there are drop packets. But the drop packets are recovered by the higher level protocols, all reliable protocols will notice there's no response and resend the packets. So the key is to recover in short enough time that you drop a minimum number of packets. Of course, if you're using UDP by definition, you've said you don't care. Devices. We need both hot pluggable and hot unpluggable or removable devices in a non-disruptive fashion. So that applies to both shared and dedicated devices. We need, one of the things the service providers will often do is walk up to a box and pull a card. And they expect that box to keep on running if it happens to be a line card or something providing network access. Only the services associated with that card should go away, but everything else should continue. In an HA environment where you've got replicated hardware, they'll pull out one of the cards that represents what we call the route processor, the RP. And if it's the active, they expect it to fail over to the standby and everything to continue. They don't expect any kind of failure. We've got to emulate this somehow in this environment if we implement software HA, which we think is a key differentiator in this environment. DOM 0. We think that all domains for our use have to be restartable. Separate device driver domains is a great idea, and we think that it's important for both scalability and reliability reasons, as have been discussed, as Jun talked about. But what we need to do there is when they restart is that it should look like a hot plug. The guests should all know that that device has reappeared. They should know how to reconnect to it, and they should know how to recover. Deterministic performance, as Edwin was talking about, one of the big issues in our space is deterministic performance, especially if we're going to do deep packet inspection and low latency forwarding. We need to be able to reliably get resources when we need them. We'll talk about how we do that, but QoS, and many of these things already exist. So many things I'm going to talk about exist and work well. I'll talk about the ones I think need to be extended or worked on. So the way we get reliable and predictable deterministic performance right now is by pinning the VMs to particular CPUs in a non-shared manner. For some applications, like for instance voicemail is a good example, it doesn't have a high bandwidth or low latency requirement. We simply allow it to be scheduled. We did some various experiments with a paravirtualized version of iOS and a 64-byte packet workload, 2 ports, bidirectional, 64 bits in with NUMA on, and this was on a Nehalem system, 8-core, 2-socket, with memory divided evenly to both sides, to both sockets. For the pin non-shared with HT off, we were able to maintain per core 100% line rate at 1 gigabit with 0.1% of the time spent in the hypervisor. So there's very little hypervisor overhead in that case. We're using all the CPU ourselves, all the resources ourselves. When we did a non-pin shared with HT off, we saw about a 10% decrease in throughput. We attribute that to scheduling. We haven't gone any farther to investigate exactly what that was, but we attribute that to scheduling, and it was NUMA was on, so the NUMA aware scheduler was doing a fairly good job as far as we could see as to which CPUs that were being scheduled for a particular VM. For pin non-shared with HT on, one of the instances on each thread, we saw about a 1.5x for I/O and 1.7x for CPU-bound applications in an aggregate throughput. The other side of that is we saw 0.75x or 0.85x on a single thread. So if your goal is aggregate throughput, then or at least for the workloads we're running, then hyper-threading is a good idea. If your goal is single transaction throughput, then hyperthreading is harmful. Pin non-shared HT on only one thread on the core in use. That appeared to have no penalty at all. That looked exactly like the first case. And so hyperthreading doesn't appear to, at least in our experiments, cost us anything as long as one of the threads is not used. The interesting thing about that is we'd like to see a way to be able to turn hyperthreading on, but fence off certain cores to only allow one thread to be used for some set of VMs. For other cores, we'd like to be able to use both threads for VMs because certain applications have particular characteristics, some that look for aggregate, some that look for per transaction. Bump in the wire looks for per transaction. Guest support, both PV and HVM, although hybrid should solve, when it's available, should solve a lot of our problems that we've tried to solve with PV. We think the hybrid solution should work just fine for us, but it's not there yet. We need both 32-bit and 64-bit guest support, simply because we have some guests that will never convert to 64-bit because of unclean code, and there's way too much of it for them to inspect and fix, and you never fix bugs by fixing them one at a time. And they're typically, a lot of these are low-end box applications. They don't have big memory space requirements. So there's no reason for them to go beyond 32-bit, and it's much too expensive to do that. Virtual memory, paged and non-paged. So OSs like iOS have a flat memory space. They come up, they define the page table as the whole memory space, and they use whatever they were given in terms of memory. There's no paging after that. There's no page faults. It's just a flat, unprotected memory space. Debug and performance monitoring. We need multi-guest, simultaneous 32-bit and 64-bit guest support with debuggers and performance monitoring. Our developers, our product developers, that's the environment they're used to. We can't go to them with a system. They can't develop their products with the same kind of tools they use today. All the tools they use today, and hopefully some additional tools, have to be available in this environment. The debugger, in several versions of Xen that we've tried, is problematic. These tools are also required in the field. One of the issues there is we have to protect them. We don't want customers running debugger in the field and doing anything with any of the applications that are running, any of the VMs that are running, but our field personnel have to be able to do that because often, one, it'd take too much time for us to replicate in our labs, set up their and duplicate their exact configuration somewhere in our labs. Secondly, we may not be able to actually duplicate the problem, and if they can duplicate it, then they have the setup to do that. And we need to be able to collect all that information in order to find out what the problem is and fix it. Trusted systems are a huge issue for both us and customers. Now it's a big topic, and there's a lot of work going on in Cisco to implement trusted systems, so that we can both verify all the software that's running on the box and validate that it's what we thought it was, especially when the customer installs a new image. And secondly, to ensure it hadn't been tampered with. Secondly, we want to do anti-counterfeiting applications that can validate that the hardware that's running on is actually the hardware we thought we delivered to run this software on. And we believe if we can have a trusted software environment, then we can trust that software environment to subsequently validate the hardware. Power management. Power management is important in some areas of the network and not others. It's especially important at edge, branch, and consumer devices. It's not as important in the core because the core is always passing packets. There's always traffic in the core. There's something going on, and it's not nearly as important to power managed. The other thing is that in certain devices and in certain application cases, you don't want to be power managed. Because even if you're not doing something right now, when a packet turns up, you want to have all the resources you need immediately. You want very low latency response to any event that occurs. So you can't afford to be scheduled out waiting for your credits to arrive while this packet's sitting there. Carrier class, Xen development environment, we think needs to support two different environments for us. One is for, and I'll describe more about this in a while. One is for rapid development prototyping. The other is for, and along with that is early product development. The second is for support of production environments. And I'll get into some details of what I mean by that. So further on HA, I think I mean something much different than was discussed in terms of HA the other day. There are two really important components. One is that in our case, HA is non-disruptive. There is all of the network links stay up and are transferred to the new active when a fault occurs. That same infrastructure is used to implement ISSU, in-service software upgrade. So in many of our accounts, it's a requirement that the vendor doesn't have an outage when either they have a fault or when they want to upgrade software. And we build the ISSU infrastructure on top of the HA infrastructure. What the ISSU infrastructure does is it implements negotiation and protocols that allow us to version messages and negotiate which versions of the message are supported between the two endpoints in various versions, and determine, first of all, if it's compatible, and secondly, if it is, then those messages will be transformed up and down as appropriate between two different versions. So we can run two different versions statefully in sync with one another, upgrade, and the upgrade process is pretty simple. You upgrade the standby, it comes up on the new version. The active then, at some command, it's actually an automated process once you start it. The active then fails over to the standby, which becomes a new active on the new version. The old active comes back up on the old version to begin with, so that if the new version doesn't perform as you want, you can fail back to the old version on command. Once you've accepted it, then the accept state simply brings a new image onto what's now the standby, used to be the old active, and now you're back in sync with two versions exactly the same. I think I've probably gone over most of this. For HA, the I/O devices always belong to the active, but have to be switched to the new active when, without a loss of state, when an event occurs that causes a switchover. Packet loss is okay, as we said. Switchover has to take place in less than a second. Many of our customers have requirements of 1/10 of a second or less. Now that's for forwarding. So there's various levels of recovery. Forwarding typically uses the existing FIB, the forwarding information base, to forward on. That's typically still completely valid, although it would be updated. It's typically still completely valid unless you've had a lot of network events and everybody's failed, and then it hardly matters. And when we've actually never seen that happen, that everybody fails at one time. Either everybody fails at one time because of a power outage, in which case none of this stuff works, or you get individual events. So I talked about ISSU. What we think is needed, there's a couple of things we've been looking at how we would implement some of this, how we'd emulate some of this stuff on Xen. Should we implement a software-only HA infrastructure? And the idea there is that software fails a lot more often than hardware. For many customers, this is sufficient for their business. It's also very inexpensive, and it's a natural fit for multi-core. We need some way to implement a reliable fast failure detection mechanism. On hardware, with replicated hardware, what that typically does is raise a pin. If it hits a fault handler for an unrecoverable fault, it raises an interrupt on the other processor, and the other processor sees the event right away, and it takes over. We could do this through software mechanisms in Xen. The issue there is we're not convinced that these will always be reliable. There's always a backup mechanism, which is based on heartbeats, but heartbeats are reasonably slow. And if the detection mechanism takes a long time, what you end up with is a lot of drop packets. Second thing is to fail over the devices transparently from the active to the standby. We can't have any loss of device state. The packet traffic can be dropped, as we talked about, but it has to be recovered quickly. Interrupts have to be redirected to the new active. We need to be able to run in a redundant hardware configuration or multi-core devices, both equally. We'll configure the drivers. For example, we've put together an experimental implementation of a lock-free queuing mechanism on which acts as a driver to IPC, which acts as the transport mechanism for checkpointing between the two endpoints. So we can configure which drivers are used, whether they use an Ethernet driver or whether they use a memory-to-memory, shared memory driver, and whether they use the network between the two endpoints or whether they use some other mechanism. We think that the recovery decisions need to be in the domain of the guest driver. The guest, in our experience, has the best view of what needs to be done. And that also minimizes the changes to the Xen kernel and DOM0. This needs to be supported for both direct assigned devices, including SRIOV, as well as shared devices, because we'll have applications that will use both. The network devices will be direct assigned. Maybe a disk will be shared with a back end running in a device driver domain. For DMA, we'd prefer a non-shared memory solution where the guest that failed was DMAing into its memory. The issue there is the VTD hardware is programmed for that device to point to the other guest. We need to be able to reprogram it either ahead of time with a missing piece of data or after the failover, which takes a lot more time for the failover to complete, such that we can repoint the VTD hardware to the new guest correctly. So this is the two development environments again. There are a couple of issues here that the rapid prototyping and product development cycle often requires an unstable branch, at least at the beginning as we're introducing prototype hardware and need prototype hardware support. Xen, we think many of our developers have found Xen very difficult to get into. Their primary interest is not in Xen itself. Their primary interest is putting out their product. That's what they're getting paid for, getting their product out to the field. Xen is just a mechanism to allow them to do some things they can't do on current hardware and software infrastructure. But from their point of view, it's just a tool. It's not the objective. And in that vein, developer threads, blogs, email, et cetera, often they don't know how to frame the question, so they get the wrong answer or they get conflicting answers. None of those answers work, and so the email goes back and forth, and it takes a week to figure out how to do something. If they're doing a fast prototyping exercise and they've got 60 or 90 days to sort of prove that something can get up and get done, that kind of is very limiting. That kind of process is very limiting. And the failure of that will mean that, or can mean, that that prototype is eliminated from the choices simply because they couldn't get there in time. Not that it wouldn't work or shouldn't work or couldn't work, or not that it's even not a good solution. Just that you can't get there in time, so on to the next one. Another problem is corporate networks and labs are often behind firewalls and use proxies. That doesn't work well with the Git-based, go to the network and get me some source kind of build. We have to go and get exceptions to corporate policy, IT policy, in order to get a link outside of the firewall to be able to do Xen builds. That takes us, in the first case, it took us 2 months. In subsequent cases, it took us a month because the guys in the new location could then talk to the guys in the old location, and some of the experience, the old guys cut down the process a bit, but it took a month, paperwork and senior VPs signing stuff and all kinds of, so it's just not a very reasonable process for us to have to go through. And a lot of people, I think Intel experienced the same thing trying to build in their labs. Most large companies have this situation. It's just not a reasonable way to do things, and for us. And there's another reason, which is on the final bullet on the next production product part of the slide, that auditing requires us to be able to reproduce an image on demand at any given time, bit for bit, from a local copy. That's an auditing requirement. We can't get away from that. The auditors can walk in at any time and say, rebuild that image, and they'll compare that image to another image, known image, bit for bit, to make sure that we can still support customers. So we have to be able to do that.